All right, so in this video, we're just gonna go over some basic operations you can do with continuous functions and, show that doing those operations still gives us a continuous function in the end. And this is gonna really kind of echo the theorems from section 9 about the convergence of sequences. So the first one here is gonna be, this is theorem 17.3. So let f be a real valued function with the domain of f contained in R. If f is continuous at x naught, then so our absolute value of f and kf for any constant k, any real constant k. Okay, and I want to remind you, okay, again, if you haven't watched the video about functions that I made early on, please do that. Because this notation is going to be something that you really want to get used to. Okay, not so like in our class and just sort of in general, it's better to think of something like absolute value of f of x as representing a single value of f and then taking the absolute value of that. So x is like some number that you're plugging in. F of x is a number, so now you're just taking the absolute value of a number. So this would just be a number in the end. But absolute value of f is the function that you get by taking the function f, and then for every input value, you assign the absolute value of f to be the absolute value of the value of f at that input. So you get a new function that way, which is just like taking the absolute value of all the values of the function f, right? And the same thing goes here, where kf is just multiplying every output value of f by k. Okay, so this is just a function. It's just the name of a function, okay? Of course, the notation is chosen very suggestively because it kind of represents the operation we're actually doing at every point in the domain of f, okay? Okay, so let's just prove this, okay? So for the first one, so we're going to just use the assumptions of the statement here. Okay, so let's show kf is continuous. Okay, let xn be a sequence in the domain of f, such that xn approaches x naught. Okay, then the limit of kf of xn equals the limit of k f of xn, which is k times the limit of f of xn, which is k f of x naught, which is kf of x naught. Okay, and I'm being very kind of pedantic about this because I really want to emphasize to you just how this notation works, right? Kf, like I said, that's the name of a function, okay? So here, what I'm doing is that I'm actually using the definition of kf, okay? Kf is a function. I'm plugging in xn. But by definition, the rule to get the value of kf at xn is just take k times the value of f at xn. So that's what this is, okay? I'm just kind of unraveling that definition. And then we know this is by theorem 9.2. Okay, so we proved early on that for sequences, right, you can multiply a sequence by a constant, and if the sequence converges, that just multiplies the limit by that same constant, right? So so then we can take the limit of f of xn, and since we assumed that f is continuous, f is continuous at x naught, right? So we assumed f is continuous at x naught, so that's why we can take the limit here. So this is since f is continuous at x naught. And then here I'm just saying, well, k times f of x naught is the same thing as kf of x naught. Okay, so that shows that's at least the kf bit, right? So let's do the absolute value thing. Well, I mean, okay. Let's see. So I'm just gonna sort of the book gives this argument in detail. I think it's probably not really worth spending too much time on, but then the limit of the absolute value of f of xn equals the absolute value of the limit. I don't think we actually ever proved this explicitly, but it's very simple. Maybe it would be a good exercise for you to do on your own. But this is the limit of f of xn, absolute value of the limit of f of xn, and then this is just absolute value of f of x naught, which is absolute value of f of x naught, right? Okay, anyway, so that's that. Okay, so that's two very simple operations. You can take a function and you can scale it by a constant, or you can take the absolute value and you'll still get a continuous function at the end. Okay, so that's two operations here, and let's just go straight into the next one here. This is about addition and multiplication. So let f and g be real valued functions, continuous at x naught. And of course, again, we're assuming that they're functions defined on some subsets of R, right? So their domains are subsets of R. Then first of all, f plus g is continuous at x naught. F times g is continuous at x naught. And f over g is continuous at x naught as long as g of x naught is not equal to 0, of course. Okay? Right. So for the first part, okay, proof. So for, right, of course, x naught has to be in the domain of both f and g, right? So both of these, right, the domain in all of these cases, right, the domain of f plus g, the domain of f times g, the domain of f over g is the intersection, right? So, okay. The domain of the resulting function is the intersection of the domain of f and the domain of g, right? So let xn be a sequence in the domain of f intersect the domain of g, right? Such that xn converges to x naught. Okay, so then, right, f of xn approaches f of x naught, and g of xn approaches g of x naught. So by theorem 9.3, we have f plus g. Let's see, I'll say it this way. The limit of f plus g of xn equals the limit of f of xn plus g of xn, which is the limit of f of xn plus g of xn, or sorry, plus the limit of g of xn, which is f of x naught plus the limit plus g of x naught. Okay, and that is f plus g of x naught. Right. So that proves right. So we just invoked the theorem we use to show that sums of convergent sequences are convergent, right? From section 9. That's really the main like substance here. And so this is just kind of using the definitions, and that shows that so 1 is proved, right? And then you know, similarly, if we were dealing with a product instead of a sum, you know, let's just tilt some of these pluses to be diagonal. So now we have f times g, and then this becomes okay. So you can multiply them too, and we have a different theorem. So 2 is proved, right? And then if we assume that that g of x naught is not equal to 0, then what, theorem 9.6, which was about dividing convergent sequences, right, shows us that we can take the quotient of these, right, and it all works out. Except, okay, there's one technicality, which is that, yeah, so this sequence, we can assume, okay, hold on. So here, let me kind of, so we can assume xn is not equal to 0 for all n, because, okay, if, or sorry, not xn, we can assume g of xn is not equal to 0 for all n, because basically if g of x naught is not equal to 0 and g of xn converges to g of x naught, then there has to come a point where, because so if the limit of g of xn, right, is not equal to 0, if we're assuming g of x naught is not equal to 0, that's the limit, right, then g of xn is not equal to 0 for all n greater than n for some n. Okay, so you can kind of truncate, right, because g of x naught is not equal to 0 in this case, and that's the limit of g of xn, you can kind of find some kind of a cutoff at the beginning after all the points where g of xn happens to be 0, and then g of xn has to be non-zero for all the points after that. So we can kind of assume without loss of generality, basically, that g of xn is not 0 for any value of n. Okay, so that's all of the theorems with the kind of algebraic, or algebraic operations and like absolute values and scaling by constants and stuff. I'm gonna call it for this video, and then in the next one I'll deal with composition of functions, and then I'll sort of discuss a little bit of how these theorems, how you can apply them to get a lot of stuff.